Okay, so you have a sort of a fill-in-the-blank kind of notes thing there. I'm not going to use those a whole lot, but in this particular case I do use it because there's a lot of pictures and it's just easier for me to give you the pictures than I expect you to draw them out. Okay, so we're continuing on with our review of grade 10 really. We're going to talk about position time graphs a little bit today, which you should have seen in grade 10, and in grade 11 we're going to go a little bit deeper, more advanced look at them. So linear kinematics is the description of motion by studying the relationships among the variables of position, velocity, and time. Those are the three key things: where something is, how fast it's going, and the time that it takes for that. Is that big enough? Okay, so looking at this little clip up top here, I'll just zoom in a bit so you can see a little bit better. I got a red car, a green car, and a blue car. The red one's the top one, the green one's the middle one, and the blue one's the bottom one. Which car is traveling at a constant velocity?
Green one.
Which one?
Green one.
Green one? How can you tell? What about it makes it look like it's moving at a constant speed? Say again? The other one's, just because it's going slower, does that mean it's moving at a constant speed? What about its movement tells you it's constant speed? It's kind of tough to tell here, isn't it, right? You almost need, what would help, Jen, if you had something? What would help to determine it? Like a table of positions, I suppose, if you had the number. I was thinking more like if you had grid lines, right? Would that help? Up there? Okay. So we think it's good. Which car has the greater average velocity? The greater average velocity. Why do you say blue?
It speeds up all the way through it. It doesn't slow down for it.
Okay. Does that mean that it has the greatest average velocity though? Might, I'm not sure. There's a more obvious answer. I'm not saying your answer is wrong, Vinny, but there's a more obvious answer. What about the blue one tells us that it has the greatest average velocity? Finishes first. It covers the same distance in the least amount of time. Exactly. Right? Overall, it's gone the fastest. Which one has the greatest acceleration? Red? Why do you say that? It starts in first. It gets up to its maximum speed faster. Okay. All of these kind of things we're going to be talking about in the next little while, but more from a graphical standpoint, because really looking at a picture like that, a little animation makes it kind of challenging. Okay, so some definitions, because scientists love to start with definitions. So the word motion implies movement from one place to another, thus position where the object is located is the most fundamental consideration in studying motion. Before you can do anything, you have to understand position. Anna, where are you? Right now, where are you? What is your position? Sitting in the classroom. Which classroom? My classroom, 236 is that under. But where? Where is room 236? In the school. And where is the school located? In Dauphin. Do we have a street address? I'm sorry, I'm picking on you. You probably don't know the street address. It's 330 Mountain Road here in Dauphin, Manitoba, and I can give you the postal code too, right? There's all these different ways of describing where you are. Position, before you can talk about how fast you're going, you have to be able to sort of figure out what their position is, right? And there are three things required to specify an object's position. And you guys don't need to write any of this, it looks like. What are those three things, do you think? How on earth did you come up with that, Jason? It's right on the paper there. An origin or a frame of reference. Okay? So the frame of reference is some arbitrary starting point. We talked about it yesterday, I think. I think we said yesterday that a frame of reference was a point that we take measurements from, right? Vinny, that was you that came up with that, wasn't it? Point where we take measurements from. Some arbitrary starting point. Some point, call it zero, that is our starting point, or origin. In math class, where the x and the y-axis meet, we call that the 0, 0, what do we call that? That's the origin, right? You didn't realize it, but in math class, you are dealing with a frame of reference. It's where everything else is measured from. The second thing that you need for position is the distance. How far away the object is from the origin. This d value here. How far away are you from the origin? Okay? The distance. This position could be described by a vector. In fact, position can be a vector quantity. And if you go and start taking linear algebra at any university, that'll be one of the things they start talking about. It's very confusing. You can think back to this and go, oh yeah, I remember that now. How far away the object is from the origin. And the last one, Jason? Direction. Right? In what direction are you? Now, generally, right? Generally, on a straight line, positive and negative numbers are used to indicate direction. Instead of right and left, or up and down, or east and west, we just use positive and negative, right? And it works nicely mathematically as well. And you should all know by now, positive numbers are to the right, negative numbers are to the left, right? Do you need to write all that down, or can you just quickly draw a number line with positive to the right, negative to the left? You can probably do that. Do you even need to write it down? If you don't know by now in grade 11 physics that to the right is positive and to the left is negative, you weren't paying attention all those years in math. But if you feel the need to write every single thing down, go right ahead of this. At some point you're going to get caught because you're not going to have time. Another example of that here. Okay. So the combination of these three things, and again they are origin, frame of reference, distance, direction. These three things make what we call the object's position. And I could have said she is 14 feet left and 8 feet up from the door, right? If the door is our frame of reference. Combination of these two things results in the object's position. That is how far away it is from a set point and in what direction. And I should point out, because it's got direction, it is indeed a vector. Okay. We don't normally talk about things in words. Normally we talk about things on a position line. So, you have there your position line. You have three things marked. Three positions. I gave you the first one. X1 is at +2. My goodness, nothing could be easier than this. X2 is at -5. And X3 is simply at +6. And when I say that X2 is at -5, what does that really mean? It means that it's 5 units to the of 0. 5 units to the left of 0. I gave you all three things. The minus is the direction, the 5 is how far, and the 0, the frame of reference, is implied. Just like the speed limit on the highway where it says 100, it really means 100 kilometers an hour with respect to the earth, right? They just don't put that. Because so, it would look kind of weird. Okay, so how can we show straight line motion? Consider the following trip, which is described in terms of a position line. Now, I spent hours with my little animation here, so make sure you watch it and say, ooh.
Hours?
Hours. Well, fractions of an hour. Pretty exciting, eh? Where did it start? I think it was supposed to start at 0. I don't even think it did that. Did it start at 0?
No.
I don't think it did. No, it started from over here, right? Let's assume it starts at 0. Then it stays there for a while, then it goes back, right? And then afterwards, I sort of drew a little thing on there. I said it started at 0. I think I lied, right? How useful is that? Well, it's pretty boring, really, but how useful is it? What are some things that aren't indicated there? Can you guys just draw that, just that little there on your number line there? I think you guys have, right? What are some things that aren't included in this description? It told me where it started, told me where it went, told me where it ended up, but there's one major thing missing. What is it? I'm going to replay it here. What's happening right there? It stops. Is there any mention of time in my little fancy animation? There is no mention of time. Okay? Just a position line like that is a big waste of time. Useless, right? What do we use instead? A position time graph. Hands up if you did position time graphs in grade 10. Most of the Dauphin local kids should say yes. Maybe not you international guys. Did position time graphs? All right. Well, this, Jason, is a position time graph. Right? What does it show? On the right-hand side, it shows position. Down here on the X, it shows the time. Okay? Sometimes these are called PT graphs, position time. Usually they call them DT or displacement time graphs. Those are interchangeable. Okay? Position versus time. This is a position time graph for the same object's motion or a similar object's motion. Okay? And it also includes time. Okay, so with your picture there, tell me what is happening in the interval 0 seconds to 1 second. What's happening from 0 to 1 second? It goes from 0 to 3, position 0 to position 3? Is that what's happening? Could you say that it's moving to the? Moving positively to a position of +3, or moving to the right? Do I have that here? Moving to the right. Right? How is it, describe its motion. Is it fast? Is it slow? Is it constant? What is it? Rapid? Why do you say that? I don't know who that was. Trent, was that you? Why do you say it's fast? So faster than the other speeds. Okay. Can you give me the exact speed? Is that a speed? 3 meters per second? Why do you say that, Victor? And it took a second, right? It went 3 meters in 1 second. Yeah, 3 meters per second. At a constant 3 meters per second, or did it speed up? Look at the picture. Is it a constant 3? Yeah, it is. How can you tell? Because it's a straight line. Now, normally, like if I'm mimicking this, right? If I start walking, I have to get up to speed, and then I'm gonna slow down, right? So normally, in everyday life, that would look like what? Like what would be slightly a bit different? I'd have to like sort of like curve up and then kind of slow down, right? Exactly. And we're going to get to those. I'll pull out my fancy motion detector here right away and we'll play with that. That's always a lot of fun. Okay, so motion to the right. What's the next question going to be? What's happening at a position of +3? What happens? What happens at +3? Turn around, isn't it? Doesn't it turn around right there? Right? How can you tell it turns around? The slope changes, right? Turns around. Does it turn around instantly?
Yeah.
How can you tell, Jason? It takes a straight line. What do you mean? Oh, so like it's going along in a positive slope and then boom, instantly it does what? Turns around, right? Is that how things happen in real life? Not really. Unless, like if I throw a baseball at a wall or something, right? Or hit it. It might be, but if you go like microscopically, like when you hit that baseball, you guys ever seen like slow motion camera of hitting a baseball or a golf club or anything?
Yeah.
Right? What happens to the ball? Like it compresses, right? Like that. So in fact, it's not a perfect peak. It would actually, it has to slow down. You can't go from like 50 meters a second to 0 without going through 49 and 48 and all the others, right? You have to actually slow down. Right? But if you look at it sort of from a zoomed out kind of thing, it's going to be peaked like that. Exactly. Okay, so the average turns around. What do you think the next question is? What's happening from 1 to 2 seconds? Again, this is all review from grade 10. I'm just making sure that everyone's sort of on the same page here. What happens from 1 second to 2 seconds? It slows down, you say? It slows down. So it's going along at 3 meters per second, and then it slows down. Does it go backwards to you? Why do you say it goes backwards? Yeah, exactly, right? You're at 3 and you end up at, let's go in red. You're at 3 and you end up at 1. You got to be going backwards, you're right. What's the slope like? How would you describe the slope? Okay, linear is true, but what? Anything else? Negative slope, which means going backwards to the left. Object moves negatively to a position of +1. Or maybe we should say, maybe that would be backwards. Right? Negative speed. It's moving backwards. Is this all review? Is this all coming back to you? I never know. It always seems so basic to me, and I have to remind myself that maybe they haven't seen it before. Is this Zoe making sense? Yeah? Because I'm not getting a lot of feedback. It helps. It hurts me when I don't know what's going on in your mind. Ashley, is this all review for you? Yeah? Okay. You guys can take off, no? No? Okay. Okay, what happens from 2 seconds to 4 seconds? Wade, what's going on there from 2 to 4? Staying the same. What do you mean by that? Like, I think you're on the right track, but...
It's not moving.
Not moving. It's stopped, is it not?
Yeah.
How can you tell it's stopped?
Straight.
Because the line is straight? Aren't those lines straight too? Do you mean the line is flat?
Yeah.
It's flat. Okay, yeah. That happens every year. I get a kid that says that straight line, but they really mean flat, right? Make sure you know the difference between straight and flat. I'm glad you brought that up. Wade and I had a little conversation in the hall. He did that on purpose just so we could, make that point, right? Good job. Yeah, well done. Okay, so the line is flat. That means it's stopped. How else can you tell? You can tell that it starts here at 1 and it ends at 1. How long did it stay there? 2 seconds. How can you tell, Jason? 2 to 4, right? 4 minus 2. I've obviously made this simple. What would you do if it was like, 2.3 and 4.5? Subtract, right? It's not rocket science here. You guys can do all this. Okay. Stopped at a position of +1. It stopped. Flat line. I should have tried to squeeze this in yesterday. Okay, I know. It's totally suck. Okay, you convinced me. Actually, I'll probably go to the test a little bit too. What happens in the interval 4 seconds to 5 seconds? Slowing down? Going, wasn't it going backwards before? Like, what do you mean by going backwards? Like, should we use the word backwards?
It goes negative again.
Okay. Goes to the left again? Yeah. We should probably say that. Backwards can be a little bit, right? It kind of implies what the opposite of what you were doing before. So be a little bit more specific. Yeah, it's going to continue moving negatively to a position of -1, right? Or moving left. When is it moving the fastest in that 5-second trip? When is it moving the fastest? Alexis, did you get one of these? Probably not, eh? What do you do? Okay. All right. You should follow along though, so you can learn something too. When is it moving the fastest?
0 to 1 second.
0 to 1 second? Why do you say that?
It goes from 0 meters to 3 meters.
So because it goes the farthest, that means in 1 second, all right?
Farthest.
So how far is it going in this? These are both 1 second intervals too, right? That one only goes 2. Okay, so Vinny's saying, you're actually looking at the numbers. Is there another more visual way that you can tell it's going faster? Say again? The length of the line? Hold it.
I was going to say it's the longest line.
This is the longest line.
I was going to like the 1 second.
So if I rotate this, can I rotate it?
But that one has a dot in the middle of it.
It is the longest one. I need to think about this for a second. Think if that means that I think you're right. I think because it's the longest line, it does mean it's going faster, although I've never thought of that before. That's not the answer I was looking for.
Oh, look at that, I got it close.
Wow. I don't know what I'm going to call that. It's kind of, do you know why the longest line? Let me go back to, I'll explain it. Let me go back to my original thought, the answer I was looking for, and then I'll explain why your thing works. It's the steepest, exactly, right? And I did this on purpose here, right? Like if you look at that, and if I just flip it, right, if I just flip it, see how much steeper that is? So because it's steeper, does that make it a longer line?
No, not all the time.
You're right. Why is it longer here? Because it's steeper.
Because all the intervals with them go down.
Exactly. Right? As long as the times are the same 1 second, then the steeper one has to be longer, right? Because it's kind of like that whole, like, you know, in a triangle, what's the longest side? The hypotenuse, right? And so if this is always 1 second, and this is kind of a representative of how far it goes, then you're right, longer line, right? Steeper. So you're right, but it wasn't what I was thinking of. And it only works when the intervals are the same. There, I got impressed today. That's pretty good. I don't know what I'll call that. I don't even know if I want to say that to other kids, other classes, because that might confuse them. I'll just, when I get to this point, I'll just put a little CC in the corner here, and then I'll just think of you in the future. How's that?
Yeah, sure.
And if it's a really smart class, then I'll mention it. Okay. Okay. So you guys fill those in right now. Give me an answer on a position time graph. What do the following represent? These are really simple. It shouldn't take you more than about 30 seconds. It'll take you longer to write them than think them. Easy? What does a positive slope line mean? Positive slope means, we should probably draw a picture there, right? Positive slope, up to the right. What does that mean? Moving to the
Right.
motion to the right, positive direction. Positive slope, motion to the right. Again, these are only true, I should point this out, only true on a position time graph. Because you know why? In about a week, we're going to be looking at velocity time graphs. Okay? I should point that out now. So, motion to the right, positive slope line. What about slope of 0? Flat line. Stopped. No motion. Stopped. Can I do this? Not just straight. Right? Straight doesn't mean, flat doesn't mean straight. Flat means flat. And a line of negative slope means? Yeah, motion to the left. Okay? Everyone should be all good with all this, not hard stuff.